Thank you. So, you know my name already. I am a co-founder and CTO of Actix. Actix is making what you would call modern software accessible to small and mid-sized enterprises in the manufacturing industry in Central Europe. So this is a complete switch, of course, from building Akka, but now we're building something that really is for normal people and not just for developers. So that's awesome. Before I start, after 4 years of struggle, the book finally came out this year. So if you don't have it yet, there's a code. You can go to rolandkuhn.com if you want to buy it. But there's also a new website since a month or two, reactivedesignpatterns.com, where the Coursera course videos, at least for my part, from the principles of reactive programming, are available. So check it out if you want to. So why do we want effect tracking in the first place? We've heard this this morning in the first presentation already, that Haskell is awesome because it separates the pure code from the impure code. In the end, what we want is referential transparency. Yeah? We want that if we have a function and we put some values into it and we get some value out of it, then if you put the same things into the same function, then you always want to get the same result back. That's referential transparency. Obviously, there are things that do not fall into this category, like reading from standard input. You make a function call, so to speak, and get something back that depends on the universe. So that's not really a real function in the mathematical sense. It's not referentially transparent. So how is this done normally? It is done by distinguishing in this way between functions that, given an input, return an output. These are supposed to be pure. Yeah? Let's ignore for now that Scala lets us do whatever we want in this function. So let's just assume that it does not do any impure things. Then, given the input, we get back the output. Versus in the lower case, we have a function, it takes some input, and then it returns something that might interact with the universe. That's why we call it I/O, input, output, and we get back not the value, the output, we get back an I/O. In the Haskell world, this function would be pure. It turns an input always into the same description of the computation, into the same I/O object that we want to evaluate. But once you have evaluated that, so when you run the I/O, the output that you get could every time be different. Yeah? It could return whatever someone typed into a console, it could return random numbers, what have you. So this basically means be careful, because the output that we get from the I/O might be different every time. It also means this is not pure. So when we run this, it can do arbitrary things. It can do dangerous things, and it can do things which depend on the order in which you do them. You send network packets, and it very much might matter in which sequence you do things. So when you return something that is of type I/O, you open up a whole new class of errors, that mistakes that a programmer can make. So the upper one is, you can also make mistakes there, but the upper one is safer than the lower one. There's one problem I see though. I/O itself is way too coarse-grained. It splits the universe basically into a sane place and insanity, but the insanity part contains vastly different things, and I would say different levels of insanity. For example, we have file I/O. This is the most obvious one. Reading from the terminal, reading from a file, writing to a file. File I/O, obviously not pure, but yeah, we need to do it. Then we have random numbers. This is not quite the same quality. It does not always return the same thing. Hence, it's not referentially transparent. We need to make it I/O, but yeah, it's not as dangerous. You cannot delete your file system with it. But then in the same category, we have killing processes, which is also I/O. But the random number, killing processes, not the same kind of insanity, I would say. Network I/O, obviously. We have shared memory. So accessing the same memory location concurrently from different threads obviously is also I/O, and that produces yet another kind of madness that inspires people to write actor systems and stuff. So yeah, it's we put this all into the same bag when we call it I/O, and that's a bit too coarse-grained. Hence, you can also split it up into different monads. You don't need to just use one. You can use different ones, but then you run into the problem that you need to combine these monads. If you want to have code that uses multiple of these effects, then the stacking of these monads, like if you do a network I/O and then a random number within it, or the other way around, that doesn't necessarily compose. So you need to build these monad transformers, and it's all ugly. I would call it a hack, essentially. But yeah, there are libraries that you can use to make this work, to make this happen, that you can fluently compose code that uses different tracking of effects and put them in a stack that's coherent so that you can evaluate them and so on. The F is one such library. And this takes away the boilerplate that you would normally need to write and makes it usable for mere humans, but it takes an awful lot of compile time. A Scala compiler could just take 1, 2, 5 minutes to compile a single file if you use this. So yeah, you have segregated the effects. That's all nice. But this is not what I'm talking about in this presentation. Because this does not fix one problem, one particular problem that I, having developed an actor framework, frequently encounter. Namely, we need protocols. We do not simply need to know which effects we do, but also in which order we do them. Yeah? So why do we need these protocols? Look at this. We have the do notation for comprehensions, doesn't really matter. We have some sort of I/O monad for files here, where we open a file, and then we close it, and then we read from it. The compiler will not be able to reject this code, even though you typically really want the lower one. But the compiler doesn't know which one is the right one. This arises because the compiler does not have enough information in this case. There's one mistake that you cannot do, just to mention that. If you move the close before the open, for example, the compiler would tell you, I don't know what F is. I don't have a handle to the file, so I cannot close it before I have opened it. But once I've opened it, I can do two different things. And these things are not the same. So once I've done the one thing, I cannot do the other thing anymore, but not the other way around. And the compiler simply doesn't know. Hence, the compiler cannot help us here. This has been a problem that's recognized. One language that has introduced it, I always forget, was this Java 7 or 8? That was 7, right? Okay, this is try with resources. By the way, the language thing. Who here self-identifies as a Scala programmer? Okay, and who as a Hascaller? Some? Okay, and the rest is probably then whatever, or I'll use whatever is needed for the project, or that kind of stuff. Okay, thanks. So this try with resources models this particular use case. Yeah, I open my resource, I open my file, for example, and then within this try block, I can use the file any way I see fit, and it's automatically closed at the end. This prevents this particular mistake from happening, unless you were stupid enough to close the resource within the try block. But I mean, that can be probably excluded by linters. I'm doing too much JavaScript. By style checkers. So this is reasonable if you just want to deal with files with resources of that kind, that you open, you do things, and then you close. That works well. However, it has a tiny problem in my book, namely it doesn't really compose in some ways that sometimes are needed. Let's say I need to read one file to then open another file, and then the other file is the one that I really want to keep. I want to keep doing things with in the end, but that doesn't work unless I keep the first file open all the time while I do this resource 2 stuff. Yeah, so this only works while it's properly nested, and the reason is that these approaches are purely syntactic. I would argue that also the do notation, the for comprehensions, they also are mostly syntactic approaches. That you write something in a closed form on the screen and you see this is the scope and nothing escapes. I can do things in here and that's fine. And so these approaches are very useful, but they don't allow for more advanced usages. So what I would argue is that we need semantics. We need the compiler to understand more about the code in order so that it can help us to write correct code. What this means is, instead of having a set of effects, we know that we are only doing file I/O, or we know that we are doing random numbers and killing processes. Yeah? So we have a set of effects, which means we have, on the left-hand side, we have a language that the program can use. This is not enough. We need to go to the right-hand side, where we need to actually form sentences in this language. Yeah, we need to have a sequence of effects where we can then understand, okay, I'm first opening, then I'm reading from the file, then I'm closing it. And the compiler then knows, okay, that's what I'm doing, and I can formulate a rule that I cannot read after I've closed. And then the compiler would be able to check it. Yeah, so we need this sequencing of effects. An example that I've dabbled with a bit is modeling session types, or modeling something that can be used to use session types on top of akka, specifically on top of akka typed. Who here knows actors? Everyone. Okay, so I don't have to explain them. Actors have externally visible actions that they perform. Most notably, they react to messages and they send messages. So I'm using them as an example for some effects that we might want to control. Now, the thing here is that in order to compose things sequentially, there is, from category theory, one abstraction that we can use for sequencing that is very amenable to this, and that is a monad. So it's not, it doesn't strictly need to have monad syntax and so on, but the way actions are sequenced is very useful. So I have an action that computes some sort of value. I have another action that uses this value to perform another action, and so on. And I can chain one after the other, and that's how I compose the behavior that my actor is supposed to execute. Like, I wait for a message, then I send another message, and then I wait for yet another message. Now you might ask, how do I track effects in this? In this presentation, I'm not going into the details on how exactly that works. I'm using something that's called an indexed monad. So what this means is, I have this sequencing of things. So I have a value, and then I flat map, and I flat map, and I flat map, or bind, bind, bind in Haskell terminology. And this thing that makes it work, the monad, has another type parameter on it. And this type parameter describes which actions have so far been performed, or would have been performed if the value would have been evaluated. So I could have accumulated there, okay, I have a program here in this actor monad, and it has already sent this message and received that message. That's my current state. And then when I flat map an action onto that, like I create another actor, then that would have the effect of creating another actor. So this is a monad instance that just has this, and I put one and the other together. The runtime aspect works just like the sequencing you normally do. When you're evaluating, first this happens, then that happens. And in addition, in the type system, in this additional type parameter of this indexed monad, we now have a list of effects. Yeah? Send, receive, and then create actor, which now is a list of 3 items in the composed action. So this is basically how it works. Looking a bit at code, this is from another example at a talk I gave previously. The details are not that important. Important is here this for comprehension, which is building up these actions that are supposed to be executed. Op process self doesn't really have an externally observable effect. It just gives me a value of my actor self reference. Op send obviously sends a message. and then opread waits until this actor here receives another message, and then it puts that into this activity logged match. Yeah. So what this does is it sends, it reads, and then the match might fail. So this is what the return type of this looks like in akka-typed session. This is a process description, hence it's called process. The self-actor ref is of type activity logged. The computed value, if successful, would be done. And the effects that happen if you run this are first we send log activity, then we read activity logged. Then there is a choice of either halting or not, which is this pattern match. And that's it. Yeah, _0 is terminal for these kind of lists. Unfortunately, I can't use shapeless H lists since I need loops. OK, so with this, you can write down code where the compiler accumulates the effects. Now, the point was, we want to know whether these effects actually make sense, so that the compiler can yell at us when we do it wrong. We do that by putting this return type on there, for example. And then the compiler would check that this method actually does what it promises. Yeah? This is one way of doing it. Or you can compose it in bigger things and so on. And then you have one global protocol that you compare things against. Now, while this is tremendously useful, I think, and it's great when it works, it has one downside. So this is using Dotty. I don't think the Scala 2 error reporting has gotten so nice yet, but I might be wrong. So here I have introduced on that line 40 another read that's not supposed to be there, just to simulate what would happen in this very simplistic small snippet of code if I make an error. Now the compiler does yell at me, so that's cool. Yeah, I cannot make this mistake. That's awesome. But the message is rather big. Thankfully, this read that's extraneous has been highlighted here by the compiler. Dotty is nice. But imagine what would happen if this was an implementation of the Paxos protocol. And then you would verify at the top level whether it works or not. If it works, great. If it doesn't, then you get to read like a megabyte of output. So it's probably not viable. So yeah. We wanted to do protocols, and what we have done on the type level are lists. And I think that is kind of what the problem boils down to. We need type level protocols. Wouldn't that be awesome? So protocols are state machines. Who here has read the TCP specification at some point in his life? Her life? OK, few people. But you know, or any such specification? Partially, yeah. So it's always specified in terms of states that either end of the connection can be in, and then transitions between these states. You have one state machine for the initiator of the connection, one state machine for the recipient of the connection, and then these state machines are designed by, in that case, the IETF such that they work together. So that's awesome. TCP works. And you need to then only make sure that my initiator abides by this spec to make sure that, OK, I can now interoperate with any other TCP endpoint on this planet. That's cool. So protocols typically are specified like that. They are state machines. Let's look at a very, very simple state machine. Yeah, we have a starting state. Then we send a registration message, which puts us into the state registration sent. Then we wait for confirmation, and then once we have received it, we are in state registration confirmed. So how could we write this down on the type level? Types in Scala need names. So I'm using things that have names here. This object register protocol extends protocol. Protocol has just requires you to give the start type. And so each of these states up there is an object. And each of the arrows in there is an implicit value. Yeah? The objects could also, they don't need to be case objects. They could be case class instances. And then you would put the, you would need implicit defs usually. to transition between them. But the thing is, we have these objects at runtime as well that are the states, and the implicits that model the connections between them. And this way, we can model a graph. Yeah? So this send registration is a transition from start.type, and as John has explained, start.type is the type that only contains the start object. So this transitions from the start object using a send effect. So we need to send a register of login, and then we can transition to the registration sent type. So this would be the first arrow going from the round to the first, yeah, what's that called? It's not a square, rectangle. And then the same thing for the second one. These transitions also transform the values. From I don't care about the start, transitions from the start to registration sent. Maybe that's useful. I have not found that useful really on the value level yet, but I've been bitten by writing down types in the past when they had no implementation. And that's finally when I understood why Phil Wadler says that types are propositions and programs are proofs. So when I can actually write this function, it's cool. So here it doesn't mean much, just a tidbit there. Okay, so how does this look like when we try to use it? So here we have this register service method that computes an operation. This operation abstracts over these two things. So it uses the system to obtain the receptionist. This is why it's encapsulated. This was for registering a service with the receptionist so that other actors can find it. Then it does the send and the read, and it yields done when it's successful. So this is an operation that has two effects, the send of register of t and the read of registered of t. And what we then do is we start a state machine. So that's this FSM thing. Yeah? And we started giving the object that specifies the protocol. So this FSM knows where on the first line, I'm in the start state. And I can only allow those transitions to happen for which I have implicit values. So if I write and then op process self, that doesn't do anything. Yeah? Because it doesn't have an effect. This arrow is implied. And then the second one, I get the self, which I need to call this register service thing. Op call is the way by which you take a operation and turn it into a process description. There's this subtle difference because processes in akka typed session have timeouts associated with them, for example, and names. So we call this with the appropriate key and self-reference. And this will verify against this protocol. Now, if I were to insert something here that doesn't belong, I put a read in here or a send of a different type or anything, then right at that line, it would complain. There's no need to give me the whole protocol. It will just say, this doesn't compile because there is an implicit not found. Who here loves implicit not found error messages from compiler? Nobody. But the cool thing is that it can be completely tailored with this @implicit not found annotation, and thereby the error message can be tweaked to say explicitly effect X, whatever it is not allowed in state Y. So the compiler gets right at the line where you make the mistake, emits an error message that says this is not allowed here. Another thing is, so after each of these and then calls, you have an object with a type. The object and the type represent the state machine at that point. You can take it, put it somewhere else. It doesn't need to be finished within the same lexical scope. You can pass it around, use it in different places, compose your program as you like. So these can actually be passed around. There is one thing that I have not yet figured out. Maybe in Dotty with implicit function types there are ways around this. For comprehensions are not yet supported. For comprehensions desugar to a very specific thing, namely you have a flat map, and then inside, if you do multiple lines, you have a flat map, and inside your flat map, and inside your flat map. Yeah, it becomes this huge thing. So it's not the flat maps are sequentially after another, and that leads to that the error reporting, even with this approach, would color the whole for comprehension, or it would color the last value that they return, depending on what the error exactly is. So the advantages would be lost. Therefore, I don't know yet whether for comprehensions are a good idea to support here, unless someone figures out how to do this. I have an idea. I had it just this morning on the taxi to use implicit functions to pass the state of the state machine to inside the next closure, like your env is doing, John, but I haven't been able to try it out yet. Okay, so I will be early because this is my summary already. So tracking the presence of effects is very useful. Yeah, you remember insanity, sanity, line between them. That's always very useful. But it's a bit limited. It allows us to catch some mistakes, but in the insanity part, it leaves too much unspecified for my taste. Tracking the sequence of effects is a way to get something that's vastly more powerful, that can help us write more correct programs, even with such horrible stuff as actor messaging, which is really impure. Really needed and useful stuff, I should say, because otherwise you couldn't build distributed systems. What I found is that syntactic approaches are useful for things that are local, but they are a bit too limiting as well. Validating accumulated effects is workable, but the error messages might really be too long. And so if we go properly all the way in and do type level state machines, that's the best I have found so far. But yeah, the search is probably not yet ended. Thank you.
Thanks. We have plenty of time for questions.
Hey, oh, maybe she's stand up. Thanks for the talk. I'm wondering if you've experimented with using duals for session types for two actors communicating to verify that they communicate correctly together.
So
yeah, okay.
Yeah, so as a background, if you have a session type that specifies how two parties talk with one another, then if you cut them in the middle, each of the state machines that you come up with are duals of each other, so a send turns into receive and so on. Yes, that is being done by a group at Imperial College. Alceste Scalas is working on things like that. And he also sent, just 2 evenings ago, his newest state that I'm not supposed to share, but he's working on awesome stuff there to make that cool. On the other hand, these binary session types with only 2 parties involved, while useful for things like modeling an SMTP exchange, are not so useful for modeling Paxos. Whether you've implemented that correctly. And for that, you need multi-party session types that are around also since 10 years or more, perhaps. And that's a bit more work, because then you need to mark out precisely on which channel you read and on which channel you send. And that is, so what I've seen from Alceste 2 days ago, he has gotten quite a bit further there, and I'm looking forward to that. But I can't talk about it. He asked me to not share it.
Thanks.
Anyone else? Okay, I guess that's it then. Thanks a lot. Yep. That was great.
Thank you.